Okay, so this video essentially is going to look at a continuation from the titration required practical, but we're going to look at the higher tier element. So it's this booklet here that we should be working on. We're going to look at strong versus weak acids. I'm then going to do a little bit on titration calculations, and then I'm going to do some exam questions as a separate video just for you to then have a little look at and practice. So we're going to look today at what strong acids are versus weak acids. And I'm going to talk a little bit about pH scale, what that means. But I'm going to start by just making sure that you've watched the reactions of acids video before you've looked at this video, because it is important that we are aware of the different types of acids. So there are three key acids that you do need to know their names and their formulas of. So we're just going to write the three acids down. So the first one is hydrochloric acid, and its formula is HCl. You've then got sulfuric acid, whose formula is H2SO4. And the final one is nitric, whose formula is HNO3. So they're the three main acids that you do need to be aware of. And what I'm hoping you can see is that they've all got one element in common, and that is indeed hydrogen. So essentially what makes something an acid is that when you add it to water, so it will ionize in water to form our H plus ions. And that's where we talked about the neutralization reaction. If you remember the ion formula for neutralization, H plus AQ is about them being dissolved in water. So when we're talking about an acid, we're talking about something that makes hydrogen ions in water. And that essentially is what pH measures, because pH stands for per hydrogen. Okay, so we are essentially measuring the amount of hydrogen ions that have in fact been formed within the solution. And that's what dictates whether something is a strong acid versus a weak acid. So I want you to have a little look at these two diagrams here. You can see I've got a strong acid here and I have a weak acid there. And I want you just to look at the two pictures. What do you notice about the hydrogen ions in each diagram? How might they be different? So what I'm hoping you're seeing is that for a strong acid, I can see that I have in fact got quite a high number of hydrogen ions there. And in actual fact, they've completely separated from the chloride ions. So that's important. Over here I can see, well, actually I do have some hydrogen ions, but some of the hydrogen still attached to the original formula, if you think of it like that. So when we're talking about the strength of an acid, what we're actually talking about is hydrogen ions. Okay, and I'm going to show you how. In the first example, I've got hydrochloric acid, so HCl. And it breaks down to form our hydrogen ions and our chloride ions. And as you can see in the picture, those hydrogen ions do what we call, they fully dissociate. Okay, in other words, they fully came away from the chloride ions, and that's what makes an acid strong. Okay, so when I'm asked the question to define what is meant by a strong acid, I am saying the hydrogen ions fully dissociate in solution. Okay, so they fully break apart. For a weak acid, so in this case, you can see here is my weak acid, it only does what we call partially dissociates. So in other words, yes, I do get some hydrogen ions and I do get some ions as well. But as you can see, that symbol there means that this process is reversible. So here in water, it will fully dissociate and separate, but I can't reverse it back. Again, that's what makes it strong. Whereas in my weak acid, only some of the ions dissociate. So we'd say the hydrogen ions partially dissociate in solution. And this process is reversible and can go back. So that is what we mean by the strength of an acid. So strong acids will fully dissociate in solution. Weak acids only partially dissociate in solution. And the pH is essentially a measure of how much dissociation has taken place. So as I've said already, pH is per hydrogen. Okay, so per hydrogen ions essentially. If I've got a lower pH value, that essentially means there is more hydrogen ion dissociation. Okay, so lower the pH, more hydrogen ion dissociation, so we'd have the stronger acid. So pH 1 to maybe say 3, for example, would be quite a high hydrogen ion dissociation. So the pH is essentially measuring the concentration of hydrogen ions you've got in the solution. And there's a maths question I've seen asked about this quite a lot, so it's important you're able to do this. So for every decrease in pH by 1, okay, the concentration of hydrogen ions increases by a factor of 10. Okay, so if I go, for example, from a pH of 7 to a pH of 4, I can see I've gone down 3 pHs. So my concentration of hydrogen ions will have increased by 10 to the power of 3. Okay, so that's how much they would have increased. If it was to a pH of 5, then that's gone down by 2, so it'd be 10 to the power of 2. If it was the other end of the scale, so let's say it's gone up from a pH of 7 to, well, if I'm going from 4 to 5, then I can see that that is in fact decreasing the number of hydrogen ions I have in the concentration because I've increased the pH. So you often get asked calculations around this, that sometimes it's linked to standard form. And there is a question that we're going to look at in the practice questions, but I just want to make sure you're aware that you need to remember that it's a factor of 10 increase every time you go down a pH. Okay. Now, sometimes you get asked questions where you've got to distinguish between what makes something a strong acid versus dilute. So explain why an acid can be strong yet dilute. And it's important we remember what our definitions of strong and weak mean and not confuse that with concentration, which is what people sometimes get confused by. So I'm going to put a little heading here that essentially says the difference between strength and concentration. And this is really important because this is how it's asked in the exam. So it is important you remember this. So we learned about concentration for paper 2 when we look at rates of reaction. Again, there's a video that goes along with that. But essentially, concentration is, how do we put this, a measure of how much acid particles, so essentially how much acid you have in a specific volume of water. And when we teach you it in rates of reaction, we talk about particles. So this is a high concentration, this is a low concentration. That's essentially what concentration is. So it's if I'm asked to just describe how I have, for example, a weak acid that is concentrated, well, so they want us to tell us how we can have a weak but concentrated acid. For the weak part, I'm going to say the hydrogen ions only partially dissociate. However, there is a large amount of acid in the specific volume of water. Okay, a large number of acid particles in a specific amount of water. So you could be asked that. So essentially concentration is basically how much you've watered down the acid. Okay, and that's what that's measuring. So if you're asked to talk about weak and concentrated, so you say it's a weak acid because it's only partially, the hydrogen ions only partially dissociate in solution, but we can have a large number of acid particles in a specific volume, which is what makes it concentrated. So let's just make sure we understand this idea of concentrated. So if I was asked a question, let me think. If I was asked a question where I had to explain, so how can you have a strong but dilute acid? Question mark. So I can have a strong acid because all of the hydrogen ions fully dissociate in solution, but it's dilute because there are less acid particles in a fixed volume. So essentially the examiner is trying to unpick with you, do you know what strong and weak acid are? Strong means hydrogen ions fully dissociate, whereas weak would mean that hydrogen ions only partially dissociate. And then it's about knowing what dilute and concentrated means. So this would be my dilute solution. So in other words, I have got less acid particles in my volume of water, which is how much I've watered it down by. Whereas concentrated would mean I've got a large number of acid particles in my fixed volume of water. So make sure you know what strong and weak acids actually mean. I do think it's one that will come up. It's definitely something I think is going to be part of the chemistry paper 1. But obviously you've got to revise everything. But I do feel this is something that potentially could come up. So we've already looked at the titration calculations before when we looked at the titration calculations booklet. So please make sure you have a little look at them. I do want to just do a couple of them with you. There's no harm in practicing these. I think the more you practice exam questions, the better, as I do think it helps break it down for you. So what I'm hoping you can see at the top of the page, you've got a variety of different calculations that you just need to know and have in the back of your head. This calculation here, for example, comes up quite a lot when it comes to reacting masses. This is the one that we're going to use for titration calculations. And these two sometimes link together. And I'll show you how they do that as we go through. But we're going to look at a practice question on titration calculations. So we'll get started. It says, a student started with 30 centimetres cubed of sulfuric acid H2SO4. So I can see in my equation I've got H2SO4 and I've got 30 centimetres cubed. I like to write the numbers around the equation just to keep me right. So we don't know the concentration of that substance. Okay, so that's something we've got to think about. She found that it took an average of 25 centimetres cubed of 0.1 concentration sodium hydroxide to neutralise the acid. So I've got my volume, 25, and I've got my concentration, which is 0.10. Now, we in lessons came up with a really daft mnemonic to try and remember everything that that we have to make sure we talk about. So we have our concentration, we have our volumes. Okay, so we've got to talk about volumes. We have to work out moles because that's an important thing as well. and we also have to think about ratio. And we said cats are verbally abusive to mice and rats. I think that was something like we came up with as a way of trying to remember the daft, all of the things I've got to think about for each of my substances. So I start off with concentration, because it's given me the concentration of one of them. So sodium hydroxide has got a concentration of 0.1, but I do not know the concentration of sulfuric acid, so I'm leaving that as a question mark. That's what I've got to get to work out. Volumes. Now, the key thing about volumes, as you can see from the triangle, is that volumes need to be in decimeters cubed. So to go from centimeters cubed to decimeters cubed, I am dividing by 1000. So in this case, I'm going to get my calculator. I'm going to do 30 divided by 1000 for my sulfuric acid. It has a volume of 0.03. And 25 divided by 1000 gives me a volume of 0.025. So I can now work out the moles for the sodium hydroxide because I've got a volume. So look at my calculation. Volume times concentration gives me the moles. So cats are verbally abusive to mice and rats. Okay. So I do 0.1 times 0.025 gives me a mole value of 0.0025 moles for my sodium hydroxide. So the last thing I have to think about is the ratio, and the ratio comes in through the equation. So I can see there is a 2:1 ratio, so 2 sodium hydroxides for every 1 sulfuric acid. So if I want to work out the moles of sulfuric acid, I'm going to have to divide that number by 2. So that's going to give me a mole value of 0.0125 for my sulfuric acid. So now I can work out the concentration, because concentration is moles divided by volume, and the volume has to be in decimeters cubed. So I take my moles value and I divide it by the volume, which I've already got from the question, and I can see that my concentration of sulfuric acid would have been 0.04. Okay, and again, they might ask you to do it to 3 significant figures, but I'm just going to do it to there to just show you exactly how you do it. So keep that down the side. So concentration, volume, moles, ratio. Concentration, volume, moles, ratio. So cats are verbally abusive to mice and rats is a way to remember. The year 11s came up with that, so hopefully that helps to keep you right. So you will have worked out, so in that case I can see my concentration here is 0.04. And it then says well, what is the concentration going to be in grams per decimeters cubed of sulfuric acid? So you can see I've got to do something to get a mass of some kind. And if you look on my previous calculation, you can see that I've got 2 calculations that involve mass. I've got mass is formula mass times by moles. I've got mass is concentration times by volume. We're actually going to use this one here, so mass, MR and moles. So put the triangle in just to keep it right. Mass, MR, moles. And if you're asked to convert, for example, moles per decimeters cubed into grams per decimeters cubed, then essentially what we're trying to think about here is this idea of mass. And that comes up through this calculation. So first thing you're going to have to do is work out the MR for the substance. So you've got H2SO4. Which we've done on the basics calculations of chemistry paper 1. So you get your 3 elements. In this case, there's 3 capital letters. I'm timesing that by 2, timesing that by 1, timesing that by 4. And that you add them all up at the end. So you get the masses. So you've got hydrogen's mass is 1, sulfur's mass is 32, and oxygen's mass is 16. but I'm timesing that by 4. So that's 64. I then add them all up, which gives me, so that should be 2, times 1 should be 2. So that gives me 98 as the total formula mass of sulfuric acid. I have worked out the concentration already from the titration. So I know the concentration of sulfuric acid is 0.04. So essentially, I've got the mass, the MR, and I times it by the concentration, which is 0.04. So 98 times by 0.04 gives me 3.92 grams per decimeters cubed. So what we're essentially doing is we're converting concentration in moles into concentration in grams, and you need the MR to do that. So we don't actually need that calculation in the end, but I'm just saying if it's a grams and you need to convert and you already have the concentration from the previous question, then to convert from moles into grams per decimeter cubed, you essentially are timesing the concentration by that of the formula mass for the substance. And that is often a sort of added on to marker to what could be a 4 marker if you've been asked to calculate titrations. So let's have a little look at some exam questions on titrations and making sure we can answer them. Again, you could try and give these questions a go, but essentially we'll go through them now. It says, which ion do all acids produce in an aqueous solution? We've got H plus, H minus, O2 minus, OH minus. So we should know already that pH acids are hydrogen ions in aqueous solutions. We've then got calcium hydroxide solution reacting with acid to form calcium chloride. I've got to complete the word equation. This is where I need to know the names of my salts and how they react with and what they're called based on which acid I use. So I can see this is called calcium chloride. The chloride tells me that it must be hydrochloric acid that I have used, and as it's a neutralization reaction because you've got an alkali plus an acid, I'm going to also make water. Okay. So these are foundation level type questions. So here, for example, we've got name apparatus A, so we know that is called a burette, not the pipette. Look for the tap. If it's got a tap, it's a burette. What is the reading on apparatus A? So burettes, remember, the volume is going down the way. So we're looking at the scale that it's given us. So that's 27.5, 27.6, I would say, from that, because you're measuring down the way. Okay, so just be prepared to look for that because you will be asked to do that in the in a foundation tier paper. You've then got your 6 marker question where it says the higher the concentration of a sample of dilute sulfuric acid, the greater the volume of alkali needed to neutralize it. Okay, the student tested 2 samples of sulfuric acid, P and sample Q, and it's asking me to describe how the student could use a titration to find out which sample is more concentrated. So I know from the question that a greater volume equals a higher concentration. So if this has a higher volume than that, then I'd say P is the concentrated sample. So we've essentially got to describe a titration. Okay, so just like we've done before, down the side I'm going to write all the things I need to remember. So I've got white tile, I've got pipette, burette, I've got my acids, I've got my alkali, swirl, rough titration. What else did we have? Rough titration, drop by drop, repeat. So that's essentially everything I want to make sure I include in the write-up. But I've also got to then say which of the samples, P or Q, would be, how would I know which of them is the more concentrated one? So let's get started. First thing I'm going to do is I'm going to measure 25 centimeters cubed, because that's what it says in the picture. Okay, up the top. Measure 25 centimeters cubed of acids using a pipette. So it's like word bingo, tick, I've done pipette, into our conical flask. Oh, I've known one I've missed off. I've missed off indicator, haven't I? Step 2, add a few drops of indicator. Okay, again, you don't need to name the indicator here, but you have to say that you add a few drops of indicator. So tick off indicator, that one's gone. Into the burette, I'm going to add my alkali, which in this case is sodium hydroxide. Again, I've got that from the question. And then I'm going to place the conical flask on the white tile. Tick, I've done white tile to see a colour change. Okay, so just make sure you almost use it like word bingo. So again, I've used acid, I've used alkali, I've used burette. So I place the conical flask on the white tile to see a colour change. I then add my sodium hydroxide. Oh goodness, sodium hydroxide drop by drop. Okay, and swirl each time it's added. So there's my swirl until I see a colour change. Okay, this is a rough titration. The first, this would be my rough titration. I would, so there's rough titration off the list. I would repeat for more accurate measurements. So again, you might want to say, well, what a rough titration is here, but you'd assume the examiner would know what that means. Now, I've not answered the question because I've got to say, well, how would they then use this to work out which of the samples is in fact more concentrated? It says the higher the concentration of the sample, the greater the volume. So I would then compare the volumes needed to neutralize the alkali or the sodium hydroxide. Oh no, sorry, sulfuric acid. This is why you need to check the picture. Sulfuric acid, higher volume equals higher concentration. And that's how I would use this process to work it out. Okay, so that's a 6 marker, but again, I would just put literally down the side things I need to keep myself right around it. So this question is about acids and alkalis. A dilute hydrochloric acid is a strong acid. Explain why an acid can be described as both strong and dilute. There's that question I talked about. So it's strong, remember, because hydrogen ions completely dissociate in water, and it can be dilute because a small amount of acid is in the fixed volume. So like I said before, the examiner is essentially working out whether you know what a strong acid essentially is. You've then got a calculation question here where it says I've got 1 times 10 to the negative 3 molar decimeter cubed of a solution of hydrochloric acid. And for that, its pH is 3. What would be the pH of 1 times 10 to the minus 5 molar decimeters cubed solution of hydrochloric acid? So I can see that the concentration of hydrogen ions is essentially getting less. So I would assume the pH is going up. And I remember that everything goes up by a factor of 10. So I can see that the difference between these two numbers here is a factor of 2. So, power of 2. So essentially it's gone up twice by a factor of 10. So if that's the case, and for that pH it's a pH of 3, then I would assume this must be a pH of 5 because it's gone up by a factor of 2. And that's essentially, I can see that means it's gone up rather than gone down. Okay, happy with that calculation, quite straightforward. This time we've got another titration question, and this question is out of 5 marks in total. It says that a student titrated 25 centimeters cubed of sulfuric acid with a 0.105 molar decimeters cubed of sodium hydroxide. So I look at my equation because they'll always give me my equation. I write down the side that cats verbally abuse mice and rats. So concentration, volume, moles, ratio. That's the 4 things I've got to remember when it comes to titration. So I've got my volume, I've got 5 titrations, I've got 5 volume readings from a sodium hydroxide. It's asking me to calculate the concentration of sulfuric acid, and I've got to use the student's concordant results, which are results that are within 0.1 of each other. I'm hoping you can see that this must be my rough titration because yes, it roughly gives me a volume and it's quite far out from all the rest. So that's almost like my practice run through to begin with, and I've then done my titration more accurately. But for this calculation, I've only to use the student's concordant results. So I can see the concordant results would be these 3 results here. So I've got to work out the mean. So 22.15, and then divide it by 3 to get it into the mean. Gives me a mean of 22.13 recurring. So that's there is my volume. So now I can start writing around my calculation. So I've got 25 centimeters cubed of sulfuric acid. So my 25 goes above my sulfuric acid. I've got 0.105 of sodium hydroxide concentration. And I've just worked out the mean volume of 22.13 for my sodium hydroxide. So now I'm going to use my little mnemonic here to keep me right. So for my sodium hydroxide, concentration is 0.105. My sulfuric acid, my concentration I don't know. I'm trying to work that one out. My volume of sodium hydroxide is 22.13. My volume of sulfuric acid is 25, but I know I've got to convert centimeters cubed into decimeters cubed. So I've got to divide them by 1,000. So 22.13 divided by 1,000 gives me a volume of 0.002213. You might get this in standard form. That's absolutely fine. Just stick with it. I'm using a basic calculator here. So that's 0.025. I can now work out the moles because moles is concentration times volume. That's my little triangle I've done loads of times before, where I've got concentration, volume, moles, and that's the calculation I'm going to use here. So 0.105 times by 0.002213 gives me a molar value of 0.00023323. I then have to look at the ratio from the original equation. So I can see it's a 2-to-1 ratio. So I'm dividing this by 2 to get the ratio, or the moles, sorry, for sulfuric acid. So 0.1161. And now I can work out the concentration, because I'm then just going to divide that by the volume. So 0.1231661, was it? I need to double check this now. Okay, and then I'm dividing that by 0.025. Gives me my concentration answer of 0.0. You see that okay? Again, they might ask me for a standard form, which they haven't in this case, so I'm probably going to do this to significant figures, and that there would be the concentration. Okay, and that's quite a complicated thing. Got lots of things to consider in that calculation. We've then got a question that says, explain why the student would use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide. And this is this idea of accuracy. So pipettes measure fixed volumes accurately, whereas the burette measures variable volumes. And we wanted to work out from this, didn't we, the concentration of sulfuric acid. So we wanted our sodium hydroxide to be in the burette, because we wanted that to be able to have variable volumes, which is what we did obviously measure. And we wanted our acid to have a fixed volume, and that's why we'd use the pipette for each of those. We've then got a question that says to calculate the mass of sodium hydroxide in 30 centimetres cubed of 0.105 molar decimeters cubed. We've got the formula mass of that, and this is essentially converting it into grams, isn't it, per decimeters cubed. So I'm going to take, I'm going to have to first of all work out my moles. So let's do the concentration, volume, moles, making sure it's all in the right units. So 30 divided by 1,000 to get it into decimeters cubed. 0.03. And then I've got my concentration, so I'm timesing that by 0.105. It gives me a molar value of 0.00315, and then I'm essentially timesing that by the formula mass, which in this case is 40. And it's telling me that 0.126 grams would be the mass of sodium hydroxide that I used. Okay, so there's some calculation questions. Give them a go. Obviously try and do them without the support first of all, see if you can do them, then see if you got them right. But I hope you found that useful. All right, thank you. Bye.